You know how your phone recognizes your face or how your bank instantly flags a weird transaction? Well, it all goes back to a foundational idea that took AI from just being a fancy calculator to something that could actually learn. Today, we're going to pull back the curtain on that idea, the multi-layer perceptron. So take a look at this. To you and me, that's a 6. Easy. But to a computer, it's just a grid of pixels, a bunch of brightness values. There's no inherent sixness to it. So the question is, how do we get a machine to recognize the pattern, the idea of a 6, from just raw data? That's the core problem we needed to solve. To get there, we have to start with the smallest possible building block, a single artificial brain cell. It's called a perceptron. Think of it like a bouncer at a club. It looks at all the incoming data, and for each piece of info, it assigns it a weight, basically how important it is. Then it tallies everything up and makes one simple call: yes or no, in or out. That's it. But here's the catch, and it's a big one. A single perceptron can only draw a single straight line to separate data. Now, for really simple problems, that's okay. But real-world data, it's messy, it's tangled. The perceptron just hits a wall. It famously can't solve what's known as the XOR problem, which is the classic textbook example of its limitation. And this wasn't just a small hiccup. It was a bombshell that rocked the entire field. In 1969, a book came out that mathematically proved this limitation was a dead end. And the result? Funding for neural network research just dried up. The field plunged into what we now call the AI winter. And for more than a decade, the dream of intelligent machines seemed to be completely frozen. So how did AI ever thaw out from that deep freeze? Well, the answer wasn't a smarter neuron. It was a smarter architecture. We figured out that the real power wasn't in the individual cell, but in how you connect them. It's all about the network. So let's see how this layered brain actually gets built. The solution was, in hindsight, beautifully simple. Instead of one neuron making one decision, what if we just stack them? This gives us the multi-layer perceptron, or MLP. It all starts with the input layer. That's the eyes of the network, just taking in the raw data. Then you have one or more hidden layers, and this is where the real magic happens, where the thinking gets done. And finally, you have the output layer, which gives you the final, much more sophisticated answer. Okay, so we've stacked our neurons, but what's the actual secret sauce? What makes these hidden layers so incredibly powerful? Well, it's their ability to do the one thing a single perceptron never could. They can bend the lines. Because think about it, if you just stack a bunch of things that can only draw straight lines, all you're ever going to get is another straight line. The trick is what you put between the layers. It's something called a nonlinear activation function. You can just think of it as a hinge or a twist that lets the network bend and fold its decision boundaries into complex shapes that can actually capture the messy patterns of the real world. Here's the best analogy I've ever heard for this. Imagine your messy, complex data is a crumpled up ball of paper with X's and O's all mixed together. A single perceptron gets to make one single straight fold in that paper. Is that ever going to separate the X's from the O's? No way, not a chance. But a multi-layer perceptron? Now that is an origami master. Each hidden layer performs a clever fold, then another, then a twist. Effectively, they work together to unfold that crumpled piece of paper. They're transforming the data into a whole new configuration, a new space where things suddenly start making a lot more sense. And once the paper is all unfolded and laid out flat in this new way, the final output layer can come in and do what a perceptron does best: draw one simple, straight line. And now, that line perfectly separates the X's from the O's. Problem solved. It's just a brilliant way to understand the power of layers. You know, this ability is so profound, it's actually backed by a famous mathematical proof called the universal approximation theorem. And what it says is kind of mind-blowing. It proves that an MLP with just one hidden layer can, in theory, learn to approximate any continuous function in the universe. It's essentially a universal problem solver just waiting to be trained. So the network has all this incredible power, this potential. But how does it actually learn how to use it? It's not magic, it's just a simple but incredibly powerful feedback loop. It learns from every single mistake it makes. The whole learning process is basically a dance with 3 steps. 1, make a guess. Data flows forward through the network and it makes a prediction. 2, measure the error. It compares its guess to the right answer to see how wrong it was. And 3, the most important part, change. A correction signal travels backward, telling every single connection how to adjust itself just a little bit to be better next time. And then you just repeat that, thousands, sometimes millions of times. This backward traveling signal is the absolute heartbeat of modern AI. It's an algorithm called backpropagation. It uses a bit of calculus to essentially assign blame for the mistake. It figures out precisely how much each and every neuron contributed to the final error, and then tells each one exactly how to adjust its weight to do a little bit better next time. It's the engine of learning. Now, this isn't just theory locked away in a lab. This simple architecture of layered neurons has been quietly powering technological revolutions for decades, often in ways that you interact with every single day. That comeback from the AI winter, it was spectacular. After backpropagation was popularized in the mid-80s, MLPs finally had an effective way to learn. And by the 1990s, they scored one of the first massive, real-world victories for AI, automatically reading handwritten zip codes for the US Postal Service. I mean, what a huge logistical nightmare, and this neural network solved it. From that point on, MLPs became the Swiss Army knife of AI, specifically for what we call structured data, the kind of stuff you find in spreadsheets and databases. They were used for everything from detecting credit card fraud to the early versions of text-to-speech, and their core concepts are still used in some of the most advanced architectures today. Just think about it. The last time you swiped your credit card, in that split second, an MLP was almost certainly analyzing over 100 variables, your location, the time, the purchase amount, looking for those subtle patterns that just scream fraud. Yep, this decades-old technology is the unsung hero that's still keeping your finances safe. And that's really the beautiful story here. You take a simple component, the perceptron, which has this one critical, almost fatal flaw. And by just stacking it in layers and giving it a clever way to learn from its mistakes, you create something that can learn to solve almost anything. It's all about the power of teamwork in layers. So I'll leave you with this thought. If this is what one of the very first, simplest neural network architectures can accomplish, what are the true capabilities of the massive, billion-parameter models we're building today? The journey has just started. What comes next is going to be fascinating.